What is structural equation modelling? Well, I think one of the first useful things to understand about SEM, as I'll refer to it, is that it isn't a single technique as such. We wouldn't want to compare it to, say, learning ordinary least squares regression or logistic regression, log linear modelling, which, although these techniques have a number of different aspects, we can think of them as, if you like, single approaches to address research questions. I think SEM is much better thought of as a general modelling framework that integrates a number of different multivariate techniques into this overall framework. It's a framework which draws on a number of different disciplines. It brings together measurement theory from psychology, factor analysis also from psychology and statistics, path analysis from epidemiology and biology, regression modelling from statistics, and simultaneous equations from econometrics. And all of these different techniques come together to form structural equation modelling as a general modelling environment. And it's also an environment which is somewhat dynamic. It is not set in stone at this point in time. It is actually often integrating new ways of fitting models as the technique develops over time. What sort of research questions would SEM be particularly suitable for addressing? Well, I think it's being a general model fitting environment. It can address many different kinds of research questions, but I think it's particularly suitable in situations where the key constructs, the key concepts that a researcher is interested in are complex and multifaceted, often relating to psychological, social psychological concepts. So these kinds of concepts can be quite difficult to measure and are often measured with error. And one of the useful aspects of SEM, as we'll see, is its ability to make corrections for errors of measurement. Other kinds of research questions that SEM is well suited to are ones which specify systems of relationships, rather than, as we may be used to if we're fitting regression models where we have a single dependent variable and a set of predictors or independent variables. Structural equation models may have numerous different outcomes or dependent variables, each of which is affecting other dependent variables in a more complex system. So if a researcher is interested in modelling a causal system, then structural equation models are particularly suitable. Another kind of research question that structural equation models are often used to address is where the researcher is interested in indirect or mediated effects. So in many research questions, we're interested in the effect of variable x on variable y. That would be thought of as the direct effect of x on y. But in many research contexts, we're interested in more complex kinds of relationships where the first variable x perhaps influences a second variable z, which then has a second effect on y. That would be seen as an indirect effect, and SEMs are very well suited to addressing those kinds of mediated research questions. Now, SEMs are known by a number of different names in the existing literature, and this can be somewhat confusing. Sometimes they're referred to as covariance structure analysis models. This relates to the fact that with SEMs we're actually analysing covariance matrices, not variables directly. We'll come on to that in later films. They're also known as analysis of moment structures. This is what gives the software, the SEM software, AMOS its name, because this is in recognition of the fact that the more modern SEMs analyse not just covariances but also means, so higher order moments. It's also known sometimes as a Lisrel model, which again takes its name from possibly the most well-known software, certainly the first software for fitting SEMs, which is Lisrel. More controversially, SEMs have been referred to as causal modelling, and they're often, certainly have historically been associated with analyses which get at causal effects. But I think that is probably a more controversial name to give to any modelling technique, because the claims for causal inference will come from the research design rather than the statistical model that we apply to analyse the data. There are many different software packages that are available for fitting SEMs, and this is a list that's changing and growing all the time. As I mentioned, the probably best known is Lisrel, which was developed by Carl Joreskog and Sorbonne, one of the first available packages. Now there are many more software packages available: M+, EQS, Amos, R is a free package, Stata, and many of these packages have more limited versions that are available for free for students to download and try to see which one is most suitable. I wouldn't want to make a recommendation for any particular software package. Each one has its own particular advantages and disadvantages. So, what is structural equation modelling? Well, there are many possible answers to that question. The one that I'm going to propose in this film is that SEM can be thought of as path analysis using latent variables. Now, this definition may not be very helpful to you if you aren't very familiar with either path analysis or latent variables. So for the remainder of the module, I'm going to run through what path analysis is and what latent variables are. So, what are latent variables? Well, most of the concepts that we're interested in social science are not directly observable. Things like intelligence, social capital, trust. It's very impossible to go and put some kind of meter into people and get a direct reading of their level of social capital or trust. So this makes these concepts hypothetical or latent, as we refer to them. We believe that they are latent within people at some level, and that they drive attitudes and behaviour, but we can't actually directly observe them. So we're in a bit of a difficult position if we can't measure these concepts that we're interested in, but fortunately we can use approaches which measure these latent variables using observable indicators, using variables that we can measure directly that we believe to be caused by the underlying latent constructs. So if we think of a questionnaire item, a question in a questionnaire that's been administered to a sample of people, this would be a good example of an observable indicator of a latent construct. So let's imagine that this question asks people how happy they are with their lives on a scale of 1 to 10. Now, some people will give higher answers or lower answers. There will be variability, variance in this variable across the individuals in the sample. Now, we don't think that all of that variability is only to do with people's level of happiness. Some of it will be. So some of the variability will be caused by variability in the true level of happiness across people, but there will be other factors that also cause variability, possibly to do with the questionnaire design, the temperature in the room, whether the question is administered by an interviewer or completed on a computer. These are all other factors that we're not really interested in what we're trying to measure, which is happiness. So some of the variability will be to do with happiness, the latent construct, but some of the variability will be due to other factors, error and unique variance. So we can summarise these ideas quite simply in this formula, the true score equation, where x equals t plus e. So here the measured variable, the observed indicator, is x, and as I said, the variability in x, is comprised of both true score and of error. So the true score is simply where the individual is on the true happiness dimension, their true underlying level of happiness. The error comprises two components. The first is what we could think of as systematic error. This is a bias where perhaps the question is phrased in a way which makes people give higher happiness ratings than their actual level of happiness. Maybe it's because it's a question administered by an interviewer and they don't want to seem unhappy because that's socially undesirable. This would be a systematic error. A random error would be one where you're just as likely to overrate as to underrate your happiness. So we can think of the systematic error as being one where the mean of the individual errors doesn't cancel out. It doesn't equal zero. Whereas a random error, you're as likely to give a higher as a lower score. So the expectation would be that the mean of the errors would cancel out and be zero. So this is all by way of saying that when we measure a variable, when we measure x, ideally what we would be able to isolate would be the t part of the variance, the true score, and to remove the error variance when we're trying to either predict t or use t as a predictor in a model. So we can now translate this true score equation into a very simple path diagram, which is key to representing structural equation models. So here we can see that the x reads over to being the observed item in the rectangle, the t reads over to being the latent variable, the true score in the ellipse, and the e reads over to being the circle at the top of the diagram, the error. And the arrows indicate that the observed score is caused by both the true score, the latent variable, and by other factors, the error. So we can encapsulate those ideas in this simple path diagram. It would be nice if we could implement this as a statistical model. Unfortunately, when we only have one indicator of the latent variable, if this is happiness, then this equation is what we would call unidentified. We have more unknown pieces of quantities that we're trying to estimate, the t and the e, we don't know what they are and we would like to estimate them, than we have known pieces of information, the x. We've measured x in our sample. We have two unknowns and one known, so we can't solve that equation uniquely. The equation is unidentified. So we can't separate the true score from the error when we only have one measure of the underlying concept. What this then tells us is that we need to have multiple indicators of our latent constructs. When we have multiple indicators, then we can start to over-identify the true score equation and estimate the quantities of t and e for each indicator. So we can apply many different kinds of latent variable models. We can use principal components analysis, factor analysis, latent class models, depending on the metrics of the observed indicators that we have in our data set. But what these are all going to do is to provide us with a summary score, a reduced set of factors or components relative to the full set of indicators that we start out with. And in doing that, they will correct for the error in each of the individual indicators and give us a better measure of the true score of the concept. We can represent this simply here with a common factor model. Here we have four measured variables. Let's think of these as questionnaire items. Again, they might be measuring happiness, different aspects of happiness. Are you happy at home, with your work, with your friends, and so on. So we've got four indicators of the same underlying latent variable, happiness. Now, because they measure the same thing, we would generally expect these variables to be correlated in our population. And that's what these double-headed arrows indicate. The curved double-headed arrows indicate that the x's are all correlated with one another. That's one way of representing what's going on here. Another way would be to do away with these correlations and add in the underlying latent variable, someone's true level of happiness, which we've here denoted as eta. In this model now we have happiness, latent variable, having a causal effect on each of the indicators, and that causal effect is what we can think of as the true score, the t part in our x equals t plus e equation. Now, if that's the case, then we also need to have error terms for each of these equations here, and that's what we show in the diagram there. So with these multiple indicators, we can apply a latent variable, in this case a factor model, and we can get empirical estimates of these key quantities. And here now the lambda coefficients there in this model we'll refer to as factor loadings, and these are the correlation between the factor, the eta, and each of the x variables. Now, if these indicators are good indicators of happiness, we would expect these correlations to be high. We would expect the correlation between a good indicator of the latent construct and the latent construct to be close to or approaching 1. So, if we are able to measure our constructs with multiple indicators, we can apply latent variable models, and this brings a number of benefits. Well, firstly, the kinds of things that we're interested in modelling in social science are generally complex and multifaceted. If we think of happiness, for example, it's difficult to come up with a single question which covers all aspects of a person's individual well-being. So we probably need to have multiple indicators to get a good coverage of the concept. As I mentioned, it also enables us to remove or at least reduce random error in the construct that we're measuring. This, I think, we can convince ourselves that removing error seems to be a good thing to do, but more formally we can demonstrate that if we have random error in a dependent variable, although it leaves the estimates in a model unbiased, these will be less precisely measured. There'll be a noisier measure with wider confidence intervals. More seriously perhaps, if we have random error in independent variables, then regression coefficients that we estimate using those independent variables will be attenuated. They will be smaller than they are in the population, systematically smaller, tending towards 0. So we will underestimate effect sizes and we will falsely fail to reject the null hypothesis. So, what is path analysis? Well, again, there are many ways that we could answer this question, but I think a key feature of path analysis, and one that makes it very appealing as part of structured equation modelling for social scientists, is that the model that you're wanting to fit to the data is represented diagrammatically rather than in the form of equations. Of course, we can represent the structured equation model as a system of equations, but we can also represent it as a diagram. And this visual aspect, again, is very appealing for social scientists who are perhaps less comfortable and less intuitive in their reading of equations. So the standardized notation of path analysis is a very important feature. But path analysis presents regression equations between our measured variables. So we're interested again in kind of systems of relationships between multiple observed variables. Now, that's important that I'm saying observed variables there, because in a standard path analysis we would not be using latent variables but variables which are directly observed. Again, perhaps single questionnaire items, other kinds of measures. A third key feature of path analysis is its focus not just on direct effects but also, as I was talking about earlier, on indirect effects and total effects. So for research questions where we don't have a simple linear model where we're estimating the effects of some set of predictor variables on an outcome, a dependent or a criterion, but we're interested in the pathways between multiple independent variables and possibly multiple dependent variables. So in this slide I'm presenting some of the standardized notation, the way that we represent different parts of the model using diagrammatic notation. We can see at the top a measured latent variable. So a latent variable would be presented as an ellipse. An observed or manifest variable, such as a questionnaire item that we might use as an indicator of a measured latent variable, would be a rectangle. An error variance or a disturbance term is a small circle, and there's a similarity with the measured latent variable there. They're both circular shaped because an error variance is also a latent variable. It's just that we are not specifying it as measuring anything in particular. It is the what's left over, the residual or disturbance term. A covariance path, where we're specifying that two variables in the model are related, are correlated with one another, would be represented as a curved double-headed arrow. This is a non-directional association. We're not specifying there is any causal link from one variable to another, but we want to indicate that they are correlated. And finally, the single-headed straight arrow represents a directional path, or what we would generally think of as implying causality in the model, a regression path from one variable to another. So here are some examples of some simple path diagrams that we could represent in equation form or using standardized path notation. In this simple diagram, we can see that the variable x has a causal effect on y, and the d term there is the disturbance term, so the error term in this model. This is essentially a bivariate regression model. We could also write this in that standard equation notation. This second path diagram is somewhat more complicated, but really is just adding in a second independent variable x2. So again, this is equivalent to a multiple linear regression with two independent variables, a dependent variable y, and an error term, which in this path diagram is labelled D for the disturbance term. Now, as I mentioned, one of the things that path diagrams, path analysis is particularly useful for is for studying not just direct effects, but also indirect effects. We can see now that we've introduced a more complex relationship between these variables, where x1 has a direct effect on x2, but x2 also has a direct effect on y. So we now have an indirect effect of x1 on y through x2. And we can use standard formulae to decompose these regression coefficients indicated by beta 1 to beta 3 into the direct, indirect and total components. So here beta 1 represents the direct effect of x1 on y, beta 2 is the direct effect of x1 on x2, beta 3 now is the direct effect of x2 on y, and beta 2 times beta 3 will give us the indirect effect of x1 on y. And we can also compute from this path diagram the total effect, which is the sum of the indirect and the direct effects between one variable and another. So if we take the sum of beta 1 and the product of beta 2 and beta 3, this will give us the total effect of x1 on y. So that's given a very brief overview of both latent variables and path analysis, and what I'm encouraging you to think about to understand what we're doing with structural equation models is that when we have a path diagram that includes latent variables rather than just observed variables, as we can see in this diagram, then we're representing a structural equation model. In the first video about structural equation models, I gave some background to what structural equation modelling is, the historical paths that led to its development, some of the key ideas and the ways that it can be applied in social science settings. In this video, I'm going to talk about some of the key ideas, terms and concepts in structural equation modelling. This is important because SEM is rather different to other areas of statistics. Some of the ideas that are important in understanding and applying SEMs are quite unfamiliar, and so it's important to have a grounding and a familiarity with these ideas before we move on to other applications. So in this video I'll be talking about path diagrams, the way that we represent equations and theories in the form of diagrams in SEMs. I'll talk about the difference between exogenous and endogenous variables. I'll talk about the way that structural equation modelling analyses not the raw data but the covariance matrix of the variables that we're interested in. I'll talk a little bit about how parameters are estimated using maximum likelihood in structural equation modelling, and I'll also go over how we apply what are called parameter constraints, how we don't always estimate every parameter in the model. Some of the parameters are fixed to values before we start fitting the model. I'll also talk about how we assess the overall fit of a model in structural equation models, and the importance of the idea of what are called nested models for assessing model fit. And I'll also talk a bit about identification of structural equation models. Again, that's something which is linked to model fit and something that we don't encounter so much in regression context that many people are familiar with. So the first thing I'm going to talk about are path diagrams, and path diagrams is one of the reasons why structural equation modelling is very appealing to many social scientists in particular. This is because social scientists don't always have such a strong grounding in mathematics and are less comfortable with reading complex equations and so on. And so path diagrams are another way of presenting the same information as we can get in an equation, but they do this visually, and that's often a clearer way of seeing what is being presented in an equation compared to Greek letters and symbols and so on. So if we write our path diagrams correctly, then we can read directly between an equation and a path diagram. They tell us exactly the same thing. So in this example here, we could write a bivariate regression equation in the usual way, where our dependent variable y is a function of our independent variable x, and we are going to solve this equation using data, and we're going to solve for the unknown parameter beta. What is the relationship between x and y? Now we can also write that same information down in the form of a path diagram, a simple path diagram in this case. So we have here y is now represented as a rectangle, x is also a rectangle. We have an arrow running from x to y in a single direction, and we have a small circle pointing into y, which represents the error term in the equation. And you can see there that there's a b above the line to indicate that the parameter represented by the straight single arrow is a regression coefficient. And this is quite clear, I think, visually, in the sense that what the model is implying, at least, is that that x causes y, and that there is some coefficient beta which summarizes what that causal effect is. And there is an error term in that equation. There are conventions for path diagrammatic notation so that we use it consistently. There are some variations in how different conventions are applied and so on, but this is the general form, where we have a latent variable is represented in the form of an ellipse. An observed variable, a variable that we've actually measured in our data set directly, would be represented as in the last slide using a rectangle. Error variances are small circles, and this is similar to a measured latent variable. It's a circular form, but it's actually a small circle now, and this indicates that these error terms are also latent variables, but we don't actually label them. These are kind of unknown or residual latent variables. We also indicate the relationships between variables using lines with arrows. A curved arrow with curved line with an arrow at each end indicates a covariance between two variables. We call this sometimes a non-directional path or an unanalyzed relationship, because this is used to show that two variables are related to one another, but our model does not specify anything about the direction of that relationship. It may be because it's not an important part of the theory, but we know that the two variables are associated. Lastly, a straight line with a single arrow at one end indicates a directional path, a regression coefficient. So we're saying if we use a single headed arrow, then we are indicating the direction of the relationship between two variables in our model. And we can put these basic symbols together to form more complex models, but ones which have a clear meaning and which can indeed be translated back into the standard equation notation. Here are some examples of some quite simple path diagrams. Here we're just looking at measurement models. These are confirmatory factor models, and we have here eta1, which is a latent variable shown as an ellipse. And eta1 here is shown to cause three observed variables, x1 to x3. And we can also think of that as eta1, the latent variable, being measured by the observed variables x1 to x3. And then at the top of the diagram we have three error variances, E1 to E3. So those are the errors for each of those equations. That eta1 is predicting x1 with some error, it's predicting x2 with some error, and so on. So that's a simple path diagram for a factor model, and that could be written as an equation, but we are in this instance using a path diagram. We can extend this to make a slightly more complicated path diagram. Now we have two latent variables, eta1 and eta2. They're essentially the same diagram as we saw in the previous slide, but now we have two latent variables, and we have six observed variables, six variables in rectangles, each one of which has an error term. Now we've also added in here a curved line with an arrow at each end. This is to show that in our model the two latent variables are correlated with one another. We're not saying anything about the direction of the relationship between eta1 and eta2. We're just saying that we think that there is some kind of relationship between them. In this path diagram, we've now introduced a theoretical statement about the direction of the relationship between eta1 and eta2. So we no longer have this curved arrow, but we have a straight line with an arrow at one end. So what we're saying here is that eta 2 is a cause of eta 1. And this again would be similar to the first diagram that we saw, a bivariate relationship, a bivariate regression with eta 1 regressed on eta 2, and we would then solve for the unknown beta coefficient above the straight line with the arrow at the end. But as I said, this is now a bivariate regression of a latent variable onto another latent variable. When we are building path diagrams and systems of equations, in structural equation modelling, we need to distinguish between two important kinds of variables, exogenous variables and endogenous variables. Now, an endogenous variable, as the name suggests, is something which is caused within the system. It's a variable that has, if you like, an arrow pointing into it. It is a dependent variable in one or more equations. An exogenous variable, on the other hand, is akin to an independent variable in that terminology. It's a variable that is not caused by anything within the system of equations that we are presenting as our SEM. That doesn't mean to say that we believe that exogenous variables are in some senses not caused by any other variables. It's simply that within our own model, the variables in the model, it doesn't have any direct cause. Now, an important part of SEM is that variables can be both exogenous and endogenous. So we can have an arrow pointing into a variable, making it endogenous, and that variable itself can have an arrow pointing at another variable, making it an exogenous variable in that limited sense, although it's now a different kind of variable because it has an arrow both pointing into it and an arrow coming out of it. And that's important because that kind of variable is a mediating variable. It's a variable which, through which another variable has an effect on a third variable. In this path diagram, which we've already seen, but this path diagram now we can distinguish what kinds of variables these are. We've got two exogenous latent variables here. They're exogenous latent variables because there is no directional path pointing into either of them. Neither of them, therefore, has an error term. This is just a correlation that we're seeing here. So these are both exogenous in the model. Again, we've seen this path diagram. We've got a new distinction that we can apply to it now, though, that eta 1 is endogenous and eta 2 is exogenous. Eta 2 doesn't have any direct paths going into it. It doesn't have an error term, whereas eta 1 has an error term pointing into it because it's got a directional path running from eta 2. So, a fundamental advantage of using structural equation models is this ability to represent our theories as diagrams rather than using notation which many social scientists are less comfortable with. Another, if you like, unusual feature of SEM is that in the conventional practice anyway, we don't analyse the raw data of the observed variables, but we analyse the variance-covariance matrix, which we'll denote S, of those observed variables. This is kind of unusual and somewhat surprising, I think, to people when they first come across it, that all the data that we need is just the set of covariances and variances of the observed variables. As we shall see in later videos, some structural equation models also use the means of the observed variables in addition to their variance-covariance matrix. So what are we doing with this variance-covariance matrix? Well, in broad terms, we are trying to summarise S, the variance-covariance matrix of the observed variables, by specifying a simpler underlying structure. So we're going to specify a model which is in some ways simpler than simply reproducing S. And our model, our SEM, in this sense, the simpler underlying structure, will yield an implied variance-covariance matrix. What I mean there is that if our model is true, then the variance-covariance matrix that we observe should look like this. It should have these numbers in each of the cells. And again, as we'll see later, this implied matrix can be compared to the one that we've actually observed. And that comparison, if it's done properly, can tell us something useful about how well our model is accounting for the data. To the extent that the implied and the observed matrices differ, then our theory, our structural equation model, is not doing a very good job of telling us how this data were generated. So a variance-covariance matrix, probably most people will be more familiar with a correlation matrix, but here we're dealing with unstandardized variables, and this matrix shows 6 observed variables, x1 to x6, and they are in both the columns and in the rows of this table. And the diagonal, which is shown in bold, indicates the variance. So the covariance of a variable with itself, in this case maybe x1 and x1, that gives us the variance of that variable. So a covariance of a variance with itself is its variance, and those are shown in bold on the main diagonal. Then we see in the other cells the covariances, which can be negative or positive in the other cells of this matrix. And you'll observe that the top part of the matrix is redundant with the bottom part. So we actually only need the lower part of this matrix. Now, an important aspect of any model fitting, and structured equation modeling is no different, is the need to estimate what the unknown parameters in our models are. The betas. What is the relationship between eta 1 and eta 2 in the population? Now there are different ways of estimating these parameters. In standard regression modeling, we would use ordinary least squares. In structural equation modeling, practice is mainly around using a technique called maximum likelihood. And maximum likelihood estimates the unknown model parameters by maximizing the likelihood, which we can denote L, of a particular sample of data. Now, L is, the likelihood is a mathematical function which is based on the joint probability of continuous sample observations. So, in essence, maximum likelihood finds what the maximum value of L is for a particular sample of data, and it does that by sort of iterating through using different values for the unknown parameters until it finds the maximum likelihood. Once that maximum has been found, then we have produced the maximum likelihood estimates for the unknown parameters. Now, maximum likelihood is appealing because it is unbiased and efficient. Now, what those terms mean are that if we have a large sample, then our estimates of the unknown parameters will be correct. They will converge upon the true values in the population. They're efficient in the sense that no other way of doing this will give us more precise estimates of those parameters. Now those two assumptions of being unbiased and efficient do themselves hinge on some other assumptions. One important one is that the data come from a multivariate normal distribution. Essentially, that requires us to be using continuous variables. So maximum likelihood is less good when we have variables in our data set that are not continuous and that we have arrows pointing into. In those situations, we need to use different estimators. But for now, I'll be focusing on the simpler case of multivariate normal data and maximum likelihood. Now, another way in which maximum likelihood is used in SEM is that not just in the estimation of the unknown parameters, but in use of the likelihood, the maximum likelihood. If we take the log of the likelihood for the model, then we can use this to test how well our model fits compared to some more or less restrictive alternative. So maximum likelihood is used in two ways in SEM. One is for estimation of the unknown parameters, and linked to that is use of the log likelihood to assess how well the model fits the observed data. Most areas of statistics that social scientists are familiar with, the focus is very much on estimating the unknown parameters in the model. We want to know what the relationship between X and Y is in the population, or possibly what the conditional association between two variables is. And so we focus on estimating those unknown parameters. This is also true, of course, in SEM, but in SEM we have an additional focus, which is on fixing or constraining parameters to particular values before we estimate our model. And that's a bit unusual for many people. So we can fix model parameters to any values, but it tends to be the case that we will be fixing parameters to be the value 0 or the value 1. Those are the most common parameter constraints that we make in SEM, and I'll come back to why we do that later. But we can also, in addition to fixing parameters to these values, we can also constrain model parameters to be equal to other model parameters. So we will still estimate those equivalized parameters, but they have to be estimated so that they are the same. The model applies that constraint on what the parameters are that are estimated. So again, that's something which is quite unusual, and we don't really see that in many other statistical techniques that we might use in social science. The main thing that we are using these parameter constraints for is for the purposes of model identification, and I will be saying some more about that soon. Now, I said that we can use the likelihood of our model to test how well it fits the data by comparing our model with another model. Now, when we do this, the two models that we compare have to be what is called nested, one within the other. So what do we mean by nested? Well, it's precisely this, that one model is a subset of the other, or the parameters in one model are a subset of the parameters in the other model. Another way of saying this is that if we have two models, A and B, then model A is the same as model B, but it just adds some additional parameter restrictions. So A is B plus parameter restrictions. To take an example here then, if model B has the form y equals A plus beta 1 x1 plus beta 2 x2 plus e, then model A will be nested if it has that same structure, but it applies a parameter constraint to the two beta coefficients that they are equal. So we now have this property that model A is the same as model B with an added parameter constraint. It is therefore nested within model B. If we consider a third model, model C though, and we now remove x2 from the model and we add z2 instead, then model C is not nested within model B because it isn't just model B plus some parameter restrictions. It has a new variable z which is not in model B. So these are, if you like, apple and pear models. We can't really in any sensible way make comparisons between the fit of model B and of model C because they include different variables. So I've said something about model fit already and the fact that it's based on the log of the likelihood of the model that we've estimated, and that we can do this comparison of model fit when the two models are nested. This is because if we take the log of the likelihood for model A from the likelihood for model B, or the log of the likelihood, then that is itself, that number is itself distributed as chi-square. And the chi-square distribution then has a degree of freedom which is equal to the difference in the degrees of freedom for model A and model B. We can therefore use this chi-square distribution to test the fit of the first model to the second model. Now, if our value of chi-square has a p-value greater than 0.05, then we will prefer the more parsimonious model, model A. Because what we're saying here in this situation is that the models are not different with regard to one another's likelihood values. That we say that the likelihoods are essentially the same. That means that we will prefer the model that is simpler and is estimating fewer parameters. So where in this case that model B would be our observed data, the variance-covariance matrix, then we're saying that there is no difference between the observed and the implied matrices, and our model therefore fits the data well. So that's the essence of the assessment of model fit using chi-square in structural equation models. We can look at the difference in the likelihood for one model and compare it to the likelihood for a nested model and make a statistical test of whether one fits the data better than the other. So the last thing I'm going to talk about in this video is model identification. This is all linked with the things I've talked about already to parameter constraints and fixing parameters to particular values and to assessing model fit and so on. So what is model identification? Well, in conceptual terms, we need to have enough known pieces of information in an equation to produce unique estimates of unknown parameters. Now we need unique estimates, otherwise we don't know which ones to prefer. So to give an example of what we mean here by the balance between known and unknown pieces of information, if we look at these two equations, the first of these is unidentified. We have x plus 2y equals 7. So what we would want to do is to find the unique value that satisfies that equation for y. Now, because we have a balance of knowns and unknowns where x and y could really take on many different values, and they would all be true, if you like, in terms of the equation being correct, that equation is unidentified because it doesn't enable us to produce unique estimates. Now, if we change that equation slightly, where we now are not having x as an unknown and we make that 3, then we can only have one value for y, which is 2, in a way that will satisfy that equation. So that equation then is identified. Now that is the essence of what we need to understand about identification, is that it's to do with the balance between the number of known and unknown pieces of information in an equation. Now there is something else to know about identification, which is that it's a theoretical property of the model. It's not really linked to the data as such, so we can figure out what the identification status of a particular model is without having any data or estimating any parameters. But it's also true to say that a model can be theoretically identified, but empirically unidentified given a particular set of data. So we are looking at the balance between the known and the unknown pieces of information in our equations, and in SEM the known pieces of information are the variances and covariances and means, if we're using means in our model, of the observed variables. These are the known pieces of information. The unknown pieces of information are the parameters that we want to estimate in the model. Now, models can have different identification status. A model can have, as we saw a moment ago, more unknowns than knowns. That means that it's unidentified. We can't produce unique values for the unknown parameters. So that's an unknown, an unidentified model. Other models can be just identified, where the number of knowns is equal to the number of unknowns. We don't have any what we call over-identifying restrictions on the model, and therefore for just identified models we don't have any likelihood for the model that we can use to assess its fit. Now, most of the models that people are familiar with using, again, ordinary least squares regression, those kinds of models are just identified. The third level of identification status is over-identified models, and that's usually what we are trying to get to and deal with in SEM, and that's where the number of knowns is greater than the number of unknown parameters in the model, and that means that we can assess the fit of the model as well as estimating the unknown parameters. So there are different ways that we can assess the identification status of a model. A very simple one these days with modern computers is simply to run our model, and most software will tell us what the identification status is of the model even before we fit the data. So it's quite easy compared to how things were done in the past. But nonetheless, it's still useful to have a consideration of the identification status of a model, as it helps us to understand where things might be going wrong if we have a problem and our model is unidentified. Working through it in this way can help us to see why. So here's the accounting rule that can be used, where if we have S as the number of observed variables in the model, and the number of non-redundant parameters is given by this equation, which is a half of S times S plus 1. Again, S is the number of observed variables, and T is the number of parameters that we are going to estimate in the model, the number of unknown parameters. So if T is greater than the answer to this equation, then our model is unidentified. We have more unknown parameters than we have non-redundant parameters. And if it's less, then we have an over-identified model. So to give an example of that, here is the path diagram that we saw earlier, where we have eta 1, a latent variable, which is measured by or causing 3 observed variables, and each of those observed variables has an error variance. So if we want to find the number of non-redundant parameters, we can use our half s times s plus 1 equation. Now we have s here is equal to 3, so s times s plus 1 is 3 times 4, that's 12. If we take half of that, it gives us 6 as the number of non-redundant parameters. Now, how many parameters are we trying to estimate with this model? Well, 3 variances, one for each error term. We've got 2 factor loadings. One of them you'll see there is constrained to 1. So we're fixing that loading, and that is for identification of the model. So we're not estimating that factor loading, but we are estimating the other 2. So we have 2 factor loadings. And then lastly, we have a variance for the latent variable. So 3 plus 2 plus 1 is 6 parameters to be estimated, which is the same as the number of non-redundant parameters. So we have, with this model, 0 degrees of freedom. The model is just identified. So we can estimate the unknown parameters, but we do not have any way of assessing the fit of this model because it's just identified, no degrees of freedom. Now, something else that's important to understand about identification is that we, as the analyst, can control to some degree the identification status of our model. So we can do this for a model like the one that we just saw that's just identified, or a model that's under-identified, by adding more known pieces of information to the equation, or by removing some unknown pieces of information, removing parameters that are to be estimated and adding constraints. So if we were to constrain 2 of the parameters in the model to be equal to one another, let's say we constrain 2 of the regression coefficients or the factor loadings to be equal, now we're only estimating 1 parameter where previously we were estimating 2. So we've removed 1 unknown and gained 1 degree of freedom. Now we can see this in this model here, where we have added an additional observed variable to the previous path diagram. So now the model is essentially the same, but we've got a 4th observed variable, x4. We now are estimating an additional factor loading and an additional error variance, but we have gained more in terms of our known parameters. So now if we use our half s times s plus 1 equation, s is now 4, so 4 times s plus 1, 4 times 5 is 20. We take half of that. Now we have 10 non-redundant parameters in this model, and we have 4 plus 3 plus 1 parameters to be estimated, 8. So 10 minus 8 gives us 2 degrees of freedom. So by adding that 4th observed variable, our model is now over-identified, and we can say something about the fit of that model to the variance covariance matrix that we've observed. So in that example, we changed the identification status of our model by adding in another known piece of information, another observed variable. Another way of changing the identification status is to remove unknown parameters. Now here, in this example, we are now not estimating the 2 factor loadings that we were in the first example. So you can see there's a number 1 next to each of the arrows for the factor loadings. So rather than estimating those, we're saying these are all equal. Now, this may not be a very theoretically meaningful thing to do. This isn't the point at this particular juncture. What we're showing here is that you can change the identification status of the model by removing unknowns. So we're not estimating these anymore. So we still have 6 non-redundant parameters, but we now are only estimating 4 unknown parameters because we are not estimating any of the factor loading. So now this model is over-identified. So in this video I have covered some of the important ideas and concepts that learners will need to take with them into later videos and applications. These are focused around the use of path diagrams for representing our theories and our equations, the fact that we analyse the variance-covariance matrix of the observed variables rather than the raw data, that we use for the most part maximum likelihood estimation, which has some quite restrictive assumptions about multivariate normality, but nonetheless is a very useful estimator. It gives us consistent, unbiased and efficient estimates of the unknown model parameters, and allows us to do global tests of the fit of the model to our data. Those kinds of fit tests are mainly applicable in the context where models are nested, where we can say that one model is a subset of a second model, that it is the same as the second model with some additional parameter restrictions. And I've talked about identification of models, and models that can be under-identified, just identified and over-identified, and how we as the analyst can exert some control over the identification status of our model by removing unknown parameters or adding in more known parameters. In the first two videos on structural equation models, I've covered some of the sort of conceptual background, the history, some of the key ideas. In this video we move to understanding some of the applications, some of the actual model fitting that goes on in structural equation modelling. And this focuses particularly on confirmatory factor analysis. So in this video I'm going to talk about the general idea of how we measure concepts using latent variables, and I'm going to contrast two approaches to using latent variables to measure concepts. The first is the more conventional, historically the main way of doing this, using exploratory factor analysis, and I'm going to contrast this then with the more modern approach of confirmatory factor analysis. I'll then move on to talking about some of the ways that we go about actually fitting and estimating confirmatory factor models, and some of the important procedures that we have to do. And I'm going to finish off by talking about some of the kind of extensions that we can take CFA into, notably when we are modelling the means of latent variables as well as their relationships, their associations. I'll talk about the difference between formative and reflective indicators in CFA, a procedure called item parcelling, and also the situation which we may sometimes be interested in of fitting a factor model to variables which are themselves latent variables, rather than to observed variables, which is the usual case, and that would be called a higher order factor model. So in the first video I gave a sort of pithy definition of structural equation modelling as being path analysis with latent variables. We can also think of this as really being a distinction between two stages or two parts of the modelling process. The first is where we want to get good measures of our concepts or our constructs. And then the second part is looking at the relationships between those measured constructs. So there's if you like, an emphasis firstly on measurement and measurement accuracy and adequacy, and then secondly, moving on to look at the structural relationships between the constructs that we've measured. So again, we saw in the first video that anytime we want to measure something in science, and particularly in social science, is that the measurements contain various kinds of error. That error can be random and or systematic. So what we want to do in our statistical approach to the data is to isolate the true score in a variable and remove the error. And this is really what we're trying to do using latent variables for measurement. So we want to decompose our x variables. X is what we've actually measured, and we can decompose that into the t and the e components. The t is the true score, and the e is the error. And we need some kind of model to enable us to split the x into these t and e components. Now, one quite straightforward and useful way of doing this is simply to add the scores across a number of different x variables. If we have, say, 4 variables which are all measuring the same underlying concept, then we could just add those up and take a summed score. Now this has some benefits because the random error in each of those measurements will cancel out as we add items together. But it's a rather unsophisticated approach, and in particular it gives equal weight to each item in the construction of the true score, and that's often something that we don't want to do. So another approach is to actually estimate some kind of a latent variable model. Now, in understanding the ways that we do this in SEM, it's useful to sort of go back in history, if you like, and think about an earlier approach to estimating latent variables. Now, this isn't to say that exploratory factor analysis is no longer used. Of course it is, but the more modern procedure of confirmatory factor analysis has some attractive properties, shall we say, compared to EFA. So the exploratory factor model is also referred to as the unrestricted factor model, or an unrestricted factor analysis, because, as we'll see when we get to looking at CFA does place restrictions on the variance covariance matrix, whereas EFA doesn't do this. EFA, or principal components analysis, is a similar technique, finds the factor loadings which best reproduce the correlations that are observed between the observed variables in our model. So let's say that we have 6 questionnaire items that all measure more or less the same thing. They're intended to measure some concept that we're interested in. An EFA will simply kind of reorder the data in a way which has best accounted for the observed correlations between those variables. Now, it does this in a way of producing a number of factors which are in EFA equal to the number of observed variables that we have. So this is really just a reordering of the observed data. We end up with the same number of factors as we have observed variables. So at this point, in just this reordering, EFA hasn't done very much in way of summarizing, of simplifying, which is often what we're trying to do with a latent variable model. So we have the same number of factors as we have observed variables, and all the variables in our model, the observed variables, are allowed to be correlated with all of the factors. Now, we need to get from this point of having the same number of factors as observed variables to retaining a smaller number, so that we're doing some job of summarizing rather than just transforming the observed relationships. And there are different rules for doing this. One kind of heuristic judgment would be to keep or retain a number of factors which is less than the number of observed variables that explain some satisfactory amount of the observed variance. So we might say we'll retain as many factors as are needed to explain 70% of the variability or the correlations between the observed variables. Something else that we have to do in addition to summarising is to understand what the factors that are produced by the factor analysis, what they mean, what are they measuring. Now we do this by looking at the pattern of factor loadings between the factor and the observed variables. So we do this in a sort of inductive way. We work out what the factors are by looking at how they are related to the observed variables. Another thing about exploratory factor analysis is that there is no unique solution where we have more than one factor, and so we can rotate the axes of our solution in ways that can help us to see what the underlying structure is. And so rotation of axes in exploratory factor analysis is quite common. Now, to give an example of what I mean by some of those previous points, here's some made up data, and we have 9 observed items, and these are, if you like, knowledge quiz items that have been administered to a sample of children. And what we're measuring is some construct like intelligence or cognitive ability. Now, if we were to apply an EFA or a principal components analysis to this data, then we would initially have 9 components or factors, which is the same number as the observed items. So the first thing that we would need to do would be to implement some judgment about how many factors to retain. Now, in this case, you can see that 3 factors have been retained in this model, and that may have been based on one of these heuristic guides around amount of variance explained, or some kind of plot, like a scree plot. So once we've done that, we want to know what each of these 3 factors is actually measuring, and we do that by looking at the pattern of correlations, and that's what are in the rows and columns of this table, between each factor and and the set of items. So if we look first at factor 1, we can see that the factor loadings or the correlations are high between factor 1 and the observed items which are measuring mathematical ability. So this is saying that if you have a high score, the higher your score on factor 1, the more likely you are to get the item math 1 correct. There's a high correlation between your score on the factor and your score on the item. For factor 2, there are high loadings on the visual spatial items and low loadings on the other items. And for factor 3, we see this other pattern where it's the verbal items that have a high score and low scores on the other. So we do this inductive process of figuring out what the factors are measuring by looking at the correlations between the factors and the observed variables once we've retained a smaller number that we think is in some ways satisfactory. So this is a very useful procedure and has been widely used in social science for many decades, but it does have some limitations. Firstly, EFA is an inductive, it's rather a theoretical procedure, and that is something which in general we are less happy with in terms of the way that we build theory in quantitative social science. So we've got a situation where the data is telling us what our theory should be, when generally we would prefer to do that the other way round. We would have a theory and test it against the data. Another unattractive property of EFA and similar techniques is that it relies on subjective judgment and heuristic rules about what's a large amount of variability to explain and so on. So there's a lot of room for subjectivity in determining what our model should be. And of course, when we are analysing data of this nature, where we have indicators of underlying concepts, it's rarely the case that we have no theory at all about which concepts the different indicators are actually measuring. We've usually written the questionnaire, indeed, with a specific intention of measuring particular concepts. So actually the more realistic and accurate assessment of what's going on here is that we're starting with a theory and then we're assessing it against the data that we've collected. So the idea that we are going from the data to the theory is not generally an accurate representation of how this procedure actually works. So given that that is the case, given that we do have a theory about how the indicators are related to the concepts, it's better to be explicit about that from the outset and then use statistical tests of those theories of measurement against the sample data that we've collected. So we can compare this approach of exploratory factor analysis with a confirmatory approach. So confirmatory factor analysis is also referred to as the restricted factor model, because unlike EFA, it places restrictions on the parameters of the model. It can't be therefore rotated. You can't rotate the solution. There is only one unique solution for the CFA. And the key difference now with CFA to EFA is that we specify our measurement model before we've looked at our data. And this is sometimes referred to as the no peaking rule. If we have a theory about how the indicators are related to our concepts, then we should set that down a priori as our theory and then test it against the data, rather than tweaking our theory as a function of the particular sample data that we happen to have. So when we do things in this way, in a confirmatory way, the key kinds of questions that we have to answer are which indicators measure or cause which, or are caused by which factors, which indicators measure or are caused by which factors. And importantly, and this is the real distinction with EFA, is which indicators are unrelated to which factors. Remember, in an EFA, we say that every variable is related in some way, is allowed to correlate with every factor. In CFA, that isn't the case. We will say that the correlations or the covariances between some of the indicators and some of the factors is zero. We'll make that as a parameter restriction. And we will also need to answer questions about the correlations between the factors, rather than leaving that as a default assumption in the model. Here we have 6 observed variables, x1 to x6. Now the first part of the model will have produced 6 factors or components. So at this stage we've already retained just the 2 factors that we think explain enough of the variability between our observed variables. But what you also see here still is that there is a single-headed arrow running from each of the 2 latent variables, eta1 and eta2, to all 6 of the observed variables. So there is we are estimating a correlation between each factor and each of the observed variables. Now what we would be looking for in this kind of situation is that some of those loadings would be large and some of them would be close to 0. So if we look at eta 1, for example, we might, in an EFA context, hope that or expect that the loadings between eta 1 and x1 to x3 would be high, of say 0.7 or above in standardized form, and that the loadings that run from eta 1 to x4 to x6 would be close to 0, and the opposite would apply for eta 2. So what we're doing there is, I say, estimating all of those relationships and expecting some pattern of high and low loadings between them. By way of contrast, the same variables and the same two factors now in the form of a confirmatory factor model, now rather than having estimates for all of those relationships between eta 1 and x1 to x6 and eta 2 and x1 to x6, we say that there is no relationship between eta 1 and x4 to x6. There's no arrow pointing from eta 1 to any of those observed variables, and the same for eta 2. There's no arrows pointing at x1 to x3. So the fact that there isn't an arrow there means that in our model we are constraining those to 0. We're not just estimating them and saying, are they nearly 0? We are specifying our model a priori to say that those paths are indeed 0. So those are the kinds of parameter constraints and parameter restrictions that I was referring to and talking about in video 2, that it's quite unusual in other branches of statistics that we use in social science to make these constraints and fix parameters to particular values. But that's why we call the confirmatory model the restricted factor model, because we place restrictions on the loadings. So sometimes, as I just gave an example of, we would fix particular parameters to 0 for indicators that do not measure or do not influence a measured variable. And the important thing to understand is that our theory of the measurement of our concepts, how we think the concepts are related to the indicators that we've selected and written if they're a questionnaire item, that theory is expressed in the constraints that we place on the model. So we're not just estimating everything, but we are placing restrictions on what the parameters, the values that parameters can take. And those restrictions, those fixing of parameters, they over-identify the model. So we are placing restrictions which give us more degrees of freedom in our model, which enable us in turn to test the fit of our model compared to the matrix that we've actually observed, S, the sample variance covariance matrix. Another way that we apply restrictions to the parameters in a confirmatory factor model is to give the latent variables a metric. Now, what I mean by that is that if we have a measured variable, we will have specified some kind of scale for respondents to answer on. So maybe it will be strongly agree is the value 1 and strongly disagree is the value 5. So the scale is 1 to 5 for that measured variable. For a latent variable, we don't have any metric. It is an unobserved variable. It's a hypothetical variable. So it doesn't have a metric on its own. We have to give it one. And there are two ways that this can be done. The first is to essentially produce a standardized solution so that all variables are measured in standard deviation units. This can be done by constraining the variance of the latent variable to 1. And this has some benefits, but the downside, of course, is that we no longer have an unstandardized solution. If we require all latent variables to be measured in standard deviation units, then they don't have any retention of the unstandardized metric that they could be given. So the second approach is to constrain one of the factor loadings to take the value 1. And by doing this, we take the scale from that particular item, which we'll call the reference item. So if we fix the factor loading of a particular item to 1, then that will be the reference item, and the latent variable will have the same scale as that item. So if it's measured again on a 1 to 5 scale of strongly agree to strongly disagree, then the latent variable will be on a scale of 1 to 5. If it's a 1 to 10 scale, the latent variable will be on that same scale. Now, this is generally preferred to the first approach of having a fully standardized solution, because we can also get a standardized solution using the second approach of fixing one loading to the value 1, and we also get the standardized solution in that approach as well. So in confirmatory factor analysis, we are interested in making good measures of our key constructs, concepts in our theories, and we are then in the next stage usually going to move on and look at the relationships between the measured concepts. And so conventional SEM is focused on the structural model, the relationships between concepts. So we are not so interested in the means of the observed or the latent variables. And in, as I say, the conventional way of doing SEM, that isn't a focus. The focus is on covariances and correlations, relationships between the variables. But there are occasions within a SEM context where we would be interested in the means of latent variables. There are two main areas where we would want to estimate latent means. The first is where we want to see whether there are differences between groups on a latent variable, and secondly, if we're interested in change over time. Perhaps if we've got a longitudinal data set, we would want to estimate the mean of the latent variable and see whether that is changing over time. So when we introduce means into our CFA, then we do this by adding a constant to the model. Actually, when you fit models in modern SEM software, this isn't a choice that the analyst has to make. It is, if you like, done underneath the hood. But this is the process that is actually implemented, is to add a constant which has the same value 1 for all cases in the model. Now, the regression of a variable on a predictor and a constant will give us the mean of that variable in the unstandardized beta of that regression. And the mean of an observed variable is the total effect of a constant on that variable. So that the total effect, as we saw in video 1, is the sum of the indirect and the direct effects. So if we now introduce a constant, which in path diagrammatic notation is represented as a triangle, and here we have the number 1 inside the triangle to indicate that the constant is 1, then we, in this path diagram, have again a y variable and an x variable. We have a direct effect from the constant to y, which has the coefficient a. We have a direct effect from the constant to x, which is b, and a direct effect from x to y, which is c. So the indirect effect of the constant on y is the product of b and c. So by adding in this constant, we can estimate the mean of x, which is simply the coefficient b, and we can estimate the mean of y by taking the sum of A and the product of B and C. That's the total effect, the sum of the direct and the indirect effects. So that's how we introduce means into our model. Now, if we've added a mean structure in, then we will require some additional identification restrictions, because we're now trying to estimate more unknown parameters. That's the latent means. So there is a question then about how we estimate and compare one mean to another. And the way we do this is by having multiple groups. So where we have more than one group in our sample, then we can fix the mean of a latent variable in one of those groups to be 0, and then the means of the remaining groups on that latent variable are estimated as differences from the reference group. So with mean models in CFA, one of the groups always has to have a restriction that their mean value is 0, then the other groups are interpreted in terms of differences from that reference group. When we've looked at path diagrams and thought about the relationship between concepts and indicators, between latent variables and observed variables, the arrow will be pointing from the latent variable to the observed indicator. So what this is saying in theoretical terms is that the latent variable causes the indicators. That's why the arrow points in that direction. So we can think of that as meaning, if we're trying to measure, let's say, someone's social capital, and we've asked lots of questions in a questionnaire, that what's actually causing their answers to those questions in the questionnaire is their underlying level of social capital. So the causal arrow points from the latent variable to the observed indicators. Now, for many concepts, that direction of causality makes sense. In other contexts, the idea that the causality flows from the latent variable to the indicator doesn't really make sense. So let's think of an example where we want to measure socioeconomic status, and we're going to use indicators of someone's level of education, what kind of occupation they have, their earnings, and so on, and we want to combine these somehow into a latent variable that measures their socioeconomic status. Now, what's problematic about this in the reflective indicators context is that it doesn't really make sense to say that I have some underlying socioeconomic status, and that if that were to change, then my educational level would change, or my earnings would change, or my occupation would change, because actually causality is flowing in the other direction if there is any causality going on here at all. So someone's level of education influences their socioeconomic status, as do their earnings. So now we're in a situation where the causality makes more sense to flow from the indicator to the latent variable. So the key point here is whether manipulating, if we could somehow change someone's score on the latent variable, would it make sense to change the score on the observed indicator? Now, for some concepts that makes sense, for others it doesn't. And in the case where it doesn't make sense, we would essentially turn the arrows round and make the arrows point from the indicators to the latent variable. And in this context, we've now got what we call formative indicators rather than reflective indicators. Now, as I said, it's a different sort of latent variable now that we're dealing with. It's essentially a weighted index of the observed indicators, and it doesn't have a disturbance term. There's no error in it. So it's not the same kind of variable as we would have with a reflective indicator. The key thing is that in the path diagram, the arrows point from the indicator to the latent variable rather than the other way round. There are, of course, some quite different procedures for estimating this kind of a model, but for now, the concern is to understand the conceptual difference and the fact that we have the indicators related differently to the latent variables. Another common procedure in confirmatory factor analysis is when a researcher may have a very large number of indicators for a latent construct or for a number of latent constructs. This is quite often the case in psychology, where there are quite complex latent variables and each one maybe has 10, 12 or more indicators. One of the problems that researchers run into with this kind of data is that the model can become extremely complex very quickly, and there's lots of difficulties that people can run into with estimation and interpretation and so on. Simply because there are so many relationships in the observed data, because there are such a large number of indicators and latent variables. And this is often combined with sometimes quite small sample sizes, which can add to this problem. So when in this situation, researchers will sometimes use an approach called item parceling, which is a first stage of taking summed scores, adding up the scores for those large numbers of items, or for subsets of those subgroups of those items, and then those subgroups of parcelled items of sum scales then act as the observed indicators for the latent variables. So this is a sort of a parsimonious way of treating rather complex data. It does rely on some assumptions about the unidimensionality of the items in that parcel, but it is an approach that researchers who are in that context of having lots of indicators for their latent variables and large numbers of latent variables can pursue. Lastly, I'm going to talk about a kind of confirmatory factor model where the latent variables are not measured by observed indicators, but are themselves measured by latent variables. So we have a sort of a hierarchical structure where a first set of latent variables are measured using observed indicators. We have to have observed indicators at some point in the model, but once that first set of latent variables are measured, then a higher order factor can be added, which is a function of the first stage latent variables. Now, this is an approach which is often useful when our theories are not so much about the relationship between variables, but are in the dimensional structure of the data. For example, in psychology, there are debates about the number of personality dimensions, and often, belief systems and so on. It's important to understand how many different dimensions that there are, in addition to how those dimensions might be related to other variables. So intelligence, personality and so on, higher order factor models can be useful. They can also be applied in a longitudinal context. So here's what a path diagram for a confirmatory factor model with a higher order structure would look like. We have at the bottom of the diagram now the observed variables in rectangles. There are 9 of those, and each set of 3 is measuring a latent variable, and then the highest level variable eta 1 is then measured as a function of those 3 latent variables. So in this third video, I've looked at some of the important issues in confirmatory factor analysis. Started off by looking at the general idea of using latent variables to measure concepts in our theories. I've contrasted the the historical approach, the conventional approach of exploratory factor analysis, or the unrestricted factor model, to the more modern confirmatory factor model, the unrestricted factor model. We've looked at how we can give a metric, a scale to latent variables by fixing one of the indicators to take the value 1 and therefore take the scale from that reference item. We've thought about how we can analyse means within a confirmatory factor model. Usually we're mainly focused on associations, correlations, but we can also estimate means. We've looked at some special cases where we have formative indicators rather than reflexive indicators, where we have a first stage of item parcelling when there are many indicators and a large number of latent variables. And we finish by the special case of a higher order factor, where a latent variable is measured not by observed items but by lower level latent variables. In the previous video, we looked at how we can use latent variable models, in particular confirmatory factor analysis, to specify what we call the measurement model, the measurement part of a structural equation model. In that component, we are seeking to get good measures of the concepts that we're interested in our theoretical model. We're wanting to assess how well we are able to measure concepts, to correct for error, and assess the overall fit of those models. In this video, we will extend from the measurement model to include what we call structural equations, which specify our theory of how our concepts are related to one another. The steps in fitting structural equation models we've already looked at in the previous videos. The idea of establishing a satisfactory measurement model. So we have a clear idea of the concepts that we're interested in that form our theoretical model. We use latent variable models, confirmatory factor analysis and so on to get good measures of those concepts. Now we want to specify how those concepts are related to one another, and this is really the part of the modelling where we are testing our causal theory. And what this really involves is specifying regression paths between the measured concepts. Now, why do we call these the structural equations? Well, the terminology here is a little bit loose. It really comes from econometrics, where the idea of a structural equation is one which embodies the formal theory of economics within the equation. The same is not so true in the context that we're considering here, general structural equation modelling, but it still maintains the same idea that the structural equations should embody our a priori theory of how the concepts are related. But in general, we won't have as strong a prior theory as we would do in the econometric context. So we are going to fit regression paths between the measured concepts, and then we will estimate the parameters of the model. This will yield beta weights for the regression equations in the normal way that we would get in a OLS regression, for example, and we would test hypotheses about the direction and magnitude and significance of those model parameters, which would be suggested by our theory. And then the last step would be to assess the fit of the model. If we have a well-fitting model, then we can be confident that our estimates of the model parameters are consistent and unbiased. So those are the basic steps. And we've already seen the measurement part of the model. So here, really, we're just extending what we saw in the previous video using confirmatory factor analysis to incorporate regressions between the measured concepts. So this is a very simple structured equation model. It's really equivalent to a bivariate regression model, where we are regressing a dependent variable on a single independent variable. But in this context, we now have latent variables rather than directly observed variables. So eta 1 here is the dependent variable, and xi 1 is the independent variable, the exogenous variable, and we have a disturbance term in that for that regression, and we're going to estimate some value for beta, which would then tell us what the relationship between eta 1 and xi are in this example. So a very simple structural equation model, just extending a regression path between two latent variables. Now we can make this system of structural equations more complex. We've done that now by adding in two more latent variables, and we now have a covariance between the two exogenous variables. That means that what we're saying is that these are they're exogenous variables, they're correlated with one another, but we aren't making any statements about our theory of the causal relationships between those variables. But we have a regression of eta 1 on xi 1 and of eta 2 on xi 2, and we also have a regression of eta 1 on xi 2. So we are including a number of different regression weights here, and that's something that is different than we would be used to in a standard OLS regression context, because we have variables which are now both endogenous and exogenous variables. So eta 1 in this example is a dependent variable in one equation, but is also a predictor, an independent variable in a second equation, because we can see we have a regression of eta 2 on eta 1. So what we can also see here is that we've introduced indirect effects, that we have potentially an effect here running from xi 2 to eta 2, which runs through eta 1. So we can estimate that sort of relationship, and we'll come to look at that in a bit more detail later. So here we have an example of a more complicated model, but this should relate to our theoretical expectations about what generated the data that we're analysing. And so we would recover the parameter estimates for the beta weights in this model, and we would check the fit of the data using the kind of indices that we saw in the previous videos. And if we have a well-fitting model, then we would make some inferences about the theory that led us to develop this model. Does the model fit the data? Do the parameter estimates support or reject the hypotheses? Another kind of model that we can fit as a structural equation model is what's referred to as a multiple indicators, multiple causes model. And there are a couple of things to note about this. You can see we have one latent endogenous variable, that's eta 1, but the predictor variables in this model are just observed variables. They're not latent. So something to note there is that a structured equation model does not have to comprise solely of latent variables. It can be a mix of both directly observed and latent variables. The sort of use and context of this mimic model, as it's known, is often to assess the measurement properties of a latent variable. And what's interesting to note here in this path diagram is that there is a regression path between the observed variable x1 and z1. So z1 is predicting the latent variable, but it's also got a regression path into the observed indicator of that latent variable. Now, we would use this as a way of testing whether that x1 variable, the observed indicator, is perhaps functioning differently for different subpopulations. So we can imagine perhaps that the three observed variables here are perhaps scores on a test. And if we find a significant beta weight running between Z1 and X1, that would tell us that depending on your score on Z1, you would have a higher or a lower probability of getting a correct answer to X1. And that would be over and above your score on the latent variable, which in this case would be some kind of ability score. And that would tell us that there's a problem with that item. It's what we refer to as differential item function, that some groups in the population will have a higher probability of getting that item correct, even controlling for their level of ability. And this can generalize to attitude scales as well as ability scales. So that's the sort of context that one might use this kind of mimic model in. Now, we've seen that the process that we follow through in structured equation modeling is to specify the measurement model, get a good fitting model, then look at estimating regression paths between the latent variables, which we use to test our theory. Then we check the fit of the structural model, and if that fits, then we say, well, our model fits the data, and we have a theory which is supported by the data. Now that might lead us to conclude that we've got the true model. This is the correct data generating model. But we need to be very careful about avoiding the temptation to make that strong conclusion. That's because with this kind of model, with observational data, there are many different potential generating mechanisms that could have produced the data and could give you equally good or perhaps even better fit. Now here's a very simple way of demonstrating that point. Here we have a simple bivariate regression of one latent variable measuring social trust on a latent variable measuring political trust. And this is using data from the European Social Survey. And you can see that from the fit statistics there that this is a well-fitting model. We have a significant beta weight there, so we find that the two concepts that political trust has a significant effect on or relationship with, to be more neutral, on social trust. So we might this might lead us to conclude that this is the true model. But of course we can simply reverse the direction of the path between social and political trust. This tells us something completely different. In fact, we reverse the causal direction that we see here. But the fit of the model and the beta weight indeed is exactly the same with this completely opposite model. So this is a caution about the strength of the conclusions that we can draw. Even when our model fits the data well, it is not necessarily the true data generating model. So, an important distinction in structural equation models is between what we refer to as recursive and non-recursive models. So all the models that we've looked at in these videos so far are recursive models. And a recursive model is a model where all of the causal effects are going in the same direction, are unidirectional, and the disturbances, the error terms, are not correlated with one another. And we can contrast this with a non-recursive model which is a model where we have some kind of feedback loop where two variables are causing each other, and therefore we have what we can refer to as reciprocal effects, or where we have correlated disturbances. So this difference is important because it has implications for model identification, and it has implications for whether we can, how we interpret and trust the correctness of the estimates that we get from our models. So here's an example of a recursive path diagram model. We have x1 causing x2, and there's a disturbance term for that equation. x2 in turn causes y1, we have a disturbance term there, and also in that equation we have x3. So y1 is regressed on x2 and x3. But here we see that all of the causal effects are going in one direction, and none of the disturbances are correlated. So this would be a recursive model. A non-recursive model, on the other hand, will have some kind of feedback loop. And here you can see that there is such a feedback loop between y1 and x1. So x1 we have here is causing y1, and y1 is causing x1. So these are reciprocal effects. And this is actually quite a plausible kind of causal mechanism. There are many examples of situations where we would expect two variables to be causing each other. We can think, for example, of economic perceptions. The more people perceive that the economy is doing well, the more that they will support the government, and the more that people support the government, the more that they may think that the economy is doing well. So there are many examples where we would want to estimate this type of equation. And we also see here that we have a correlation between the two disturbance terms, the errors in those structural equations. And that's indeed implied by the fact that we have this reciprocal causal effect between y1 and x1 means that the disturbances must be correlated. Now, there are some grey areas, and this results in what we refer to as partially recursive models. Here we see that we have a correlation between the disturbance terms, but we don't have any direct effects amongst the endogenous variables in this model, the endogenous variables here being y1 and x1. So in this case we can treat this in terms of identification as a recursive model, but here we do, in this diagram, we have a direct effect amongst the endogenous variables. We have a regression of y1 on x1, and we then also have this disturbance term correlation. So this would be treated as a non-recursive model. Now, I said that recursivity, or recursive versus non-recursive model status, is important for identification, but that's not terribly interesting from a sort of analytical perspective. Recursivity is also important, really, because a recursive model is always identified and it's simple to estimate. We can estimate recursive models using OLS, using a set of OLS models. But that simplicity is also rather restrictive. It means that we can't estimate the more complex kinds of models that we would often want to. So introducing a non-recursive model means that we have more flexibility in the kinds of model specifications that we can use. And these are actually a lot of the reasons why many analysts want to use structural equation modeling software, because it's actually very easy to specify this kind of model. But we have to be aware that just because we can specify a model as a path diagram and we will generate some parameter estimates, that doesn't mean that we can always trust them as being valid estimates. So non-recursive models, despite being more flexible, also can be challenging in terms of identification, and will often require, in order to achieve an identified model, we will need to use other variables in the model which may not be of direct substantive interest in the model, but we need them nonetheless for identification purposes. So, as I said, if we have a model, it may be empirically identified. It doesn't mean necessarily that we can trust the parameter estimates. And in particular, if we want to have unbiased and consistent estimates for reciprocal paths, these are when we have arrows running between two variables in a model, we have to make some quite strict and some would argue often implausible assumptions about the variables in the model. So in particular, in this sort of context with reciprocal effects, we need to assume that we have some exogenous variables in the model that we can treat as instrumental variables. And this is another important idea for understanding and implementing this kind of non-recursive model, the idea of an instrumental variable. And to understand what we mean by an instrumental variable in this context, it's useful first to understand another concept, which is that of an endogenous regressor. And here we've got a simple path diagram to help understand what we mean by an endogenous regressor. So we have here y1 regressed on x1. We want to estimate beta. We'd ideally like to treat beta as the causal effect of x1 on y1. But we also see here that we have a covariance or a correlation between the disturbance term in this equation and x1, which is the predictor. Now, we know from our OLS classes that this is an assumption that we have to make in OLS, that we don't have a correlation between the error term and the predictors. If we find that there is such a correlation, then we have what's referred to as an endogenous regressor. The x1 is an endogenous regressor. And this is because, it can be for a number of reasons, but will often be because of some unobserved variable that we should have in our model that maybe is related to both x1 and y1, or it may be because of simultaneous causal effects, that x1 is causing y1 and y1 is causing x1, the sort of reciprocal effects that we're interested in here. That would generate this correlation. So when we have this kind of a situation, we need an instrumental variable for x1 if we want to be able to interpret the beta coefficient as the causal effect of x1 on y1. So an instrumental variable is a variable that's going to deal with this endogenous regressor problem, and it does this by introducing exogenous variability into the endogenous regressor. And to have the properties of an instrumental variable, then which we'll refer to as Z, our instrumental variable will be Z in this context, the instrument must cause the endogenous regressor, but not cause the outcome. Now, there are lots of different examples of instrumental variables that have been used in the empirical literature, and we'll come on to some of those. But one good way of thinking about an instrumental variable is the assignment variable in a randomized control trial. The randomization which determines whether someone is allocated to the treatment or to the control condition. This is a perfect instrumental variable because it's very strongly correlated with whether you are in the treatment or the control group, but it is uncorrelated with whatever the outcome is in the randomized control trial. So that's a good way of thinking about what an instrumental variable is, and the sorts of variables that we will be looking to use as instruments should come as close as possible to that sort of randomization type of variable. So this is what we're looking for in terms of a path diagram here. We've got an endogenous regressor x1, and we need an instrument, which is z1 here, which causes x1 but doesn't cause y1 other than through its effect on x1. So you can see it has an indirect effect on y1 but not a direct effect. So this would be an instrumental variable. As I said, there are many papers, particularly in economics, which have used natural variability, natural experiments, if you like. And one example is the Vietnam lottery draft, which determined whether US citizens were allocated to go to Vietnam or not. This was done on the basis of a random lottery. So if you want to assess the effect of going to Vietnam on later outcomes like your earnings, your education, your mental health and so on, then you can use that initial lottery draft as an instrument for going to Vietnam War. Another one that's been used is proximity to your nearest college for studying the effects of education on earnings. Obviously, if you just look at the relationship between education and earnings, there are many unobserved variables that would mean that you couldn't just take the simple correlation between education and earnings as a causal effect. But if you can use something like proximity to a college, that can have a direct effect on education, but not a direct effect on your earnings other than through its effect on education. The third example might be variability in the compulsory schooling age. This can vary across geographic boundaries. In US states, for example, have different compulsory schooling ages, or in the UK there was an increase in the compulsory schooling age from 15 to 16 in 1973. And this can be used as an instrument for, again, the effects of education on later outcomes such as earnings, because the policy change introduced random variability into how much schooling people obtained, but it wouldn't have had any direct effect on earnings. So those are some examples of instrumental variables, and it should give you an idea that you have to meet some quite strict requirements to be a good instrumental variable. And even for these three quite well-known examples, there have been criticisms of these as whether they really are valid instruments. So again, this is something of a caution, because non-recursive models are easy to specify. Here's an example, again using the European Social Survey data, where we're looking at the relationship between life satisfaction, happiness and social trust. Scholars have been interested in what the relationship is here, and this model specifies reciprocal causality between these variables. Now, if you just try to estimate that model without the two exogenous variables at the bottom of the diagram, whether you're married and your earnings, it would be unidentified. So these variables are acting as instrumental variables in the model, but it's not really plausible to assume that they are valid instruments, because we have to assume that neither of them has a direct effect on the other latent variable in this model. Each one only causes one latent variable, but it's not really reasonable to assume that your income is not related to your level of social trust. We know that's an implausible assumption. So we have to be careful. Just because we can estimate and we get parameter estimates for a structural equation model which is non-recursive, we have to check our assumptions that are needed to make that identification and assess whether we can really trust the estimates. So one of the main kinds of models that analysts will use structural equation models for are for mediation kinds of models. One can estimate mediation models in other modelling frameworks, but SEMs are particularly well suited to mediation models. What we are talking about really here is a focus on not simply the direct effect of one variable on another, which is what we are implicitly focusing on and often explicitly focusing on in an OLS context, but we want to decompose the effects of one variable on another into those direct effects, but also effects that are running through other variables in the system. So we are going to be interested in the indirect as well as the direct and the total effects. And this is because oftentimes what we are interested in is understanding causal mechanisms, not just whether two variables are causally related, but how they are causally related. So we might, for example, conclude that gaining a degree at university increases your earnings. It might have a causal effect on your earnings in later life, and that's a useful and interesting conclusion to be able to draw. But there might be secondary questions about how that actually happens. What is the mechanism that underlies the earnings return to gaining a degree? From a sort of a human capital perspective, we might expect this to be through increasing the individual's skill level or their productivity, which would then, from economic theory, lead us to expect them to have higher earnings. On the other hand, from a more kind of sociological perspective, it might just be that the degree is just a credential, and that it hasn't really endowed the individual with any greater skill or productivity, but it's just given them a certificate which enables them to get to the top of the queue ahead of people who don't have that degree. And those kinds of mechanism questions are often very important for policy and are at the heart of what we're doing when we're fitting mediation models. We've seen a couple of examples of path diagrams with mediation already. Here we see an example where we have eta 2, a latent variable, which is regressed on eta 1, and we have a third variable z, which is our kind of exogenous variable here, and we can look at the different effects that x has on eta 2. First of all, the direct effect of z on eta 2 is the beta weight beta 3 here, the direct path. So that's what we would normally be focusing on in a regression equation, that direct effect. But we can also estimate the indirect effect here, because we've got the beta 1 coefficient of eta 1 on z and the beta 2 coefficient of eta 2 on eta 1. Now if we take the product of those two parameters, then that will give us the indirect effect of z on eta 2. So that's how we can algebraically recover the indirect effect of one variable on the other, is taking the product of the two beta weights. And then we will perhaps be interested in the total effect. And this is the sum of the indirect and the direct effect. So we might find, for example, that both direct and indirect effects are non-significant, but there is still a significant total effect. So we can get different patterns of and understandings of an effect of one variable on another by looking at these different effect parameters. We sometimes distinguish between partial and perfect mediation. So for example, if we fitted a model that just regressed eta 2 on Z and we found a significant and substantial effect there, then if we add in the eta 1 predictor, if the effect of Z now becomes non-significant, but the indirect effect is significant, then we would refer to this as perfect mediation. All of the effect of Z on eta 2 flows through eta 1. Where there is still a residual effect, i.e. a significant path between Z and eta 2, that would be referred to as partial mediation. Now, as I said, we can specify these kinds of models using a series of OLS models, and we can recover the indirect effects by taking the product of the respective direct effects to get the indirect and total effects. One of the advantages of doing this in a SEM framework using SEM software, however, is that those kind of calculations are done for you and just provided in the output. And additionally, there are various ways of directly calculating the standard errors of those indirect paths. So we can either calculate the standard errors for these mediated paths using what's called the delta method, a parametric approach, which assumes multivariate normality, or more commonly now using non-parametric approaches like bootstrapping, resampling from the sample data to generate an empirical sampling distribution. If we do that, of course, we need to have the raw data rather than the covariance matrix. So the SEM framework is very convenient for doing this kind of modeling. We can have more complex mediated paths that run not just from one variable through another to a third variable, but through several variables, and we can get estimates of those indirect and total effects and their standard errors. Here's an example again using the European Social Survey, an actual model here where we are looking at the effect of being in a high income group, your income on your level of social trust, and breaking that down into the direct effect of income on social trust through and also the indirect effect through your level of happiness or life satisfaction. And you can see here that the beta weights on the path diagram there indicate that there are these are standardized parameter estimates. So you can see that there is an effect of being high income on social trust, and there seems to be an indirect path there. So we could just take the product of the 0.09 and the 0.35 parameters to get the indirect effect. If we do that, we get a figure of about 0.32, which if you look at this slide here, you can see this is some output from Amos software, and you can see there that in red the indirect effect of the column variable, which is high income, on the row variable, which is social trust, is 0.032, which is the product of those two coefficients to give you the indirect effect. And you can see that all of the possible path estimates are provided there directly in the output. Also in SEM software, you will get, as I said, the standard errors either through bootstrapping or parametric estimation, and here we see that the two-tailed p-value for that indirect effect of income on social trust is significant at the 95% level of confidence. So we could reject the null hypothesis that there is no indirect path between income and social trust. So that's a very brief look at the way that we can fit mediation models and what some of the advantages are of doing this within a SEM context. It's important to remember a couple of limitations here. One is that in this kind of modelling environment, we're really limited to continuous mediating variables. It's very difficult to estimate these kinds of models when the mediator, when the Z variable is continuous, and when we have a mix of continuous and categorical variables. It's also really not a framework for the kind of clean causal effect estimates that we were talking about in the previous video on instrumental variables. Really, this is just decomposing covariances. There are other approaches that have a more of a causal estimate focus, using the sort of the potential outcomes framework, and that would be using G computation and so on. We won't be covering those in this video, but it's important to be aware that there are other frameworks for estimating these kinds of mediation models, which are a bit more modern and have a more robust causal inference behind them.